We are looking today at Robonaut, Canadarm, and really talking about technology. I want to share this anniversary video from NASA's 60th regarding what we've done in the first 60 years of technology.
NASA has blazed a trail for all of humankind.
We have done really incredible, ambitious missions, robotic missions that make new scientific discoveries and essentially rewrite textbooks every year on a regular basis.
The computer that was used during the Apollo era, the Apollo guidance computer, allowed for 85,000 instructions per second. Our high-performance spaceflight computing platform will allow for 15 billion instructions per second. So a faster computer.
We gotta try to get there faster, if possible, with new rocket technology.
We carry more payload than any other rocket. NASA is working on this larger rocket to carry what we need to build platforms to do our deep space journeys. So onto Mars, or back to the moon, or around the moon, which is part of our initial set of missions.
We look at technologies that will get us there, land us there, and once we get there, we have to be able to explore.
There are other technologies we're looking at that would allow you to kind of suit up immediately and go straight out the door, which is something that our astronauts right now would love to do. You know, we've been taking the lessons we've learned from current white suit, and we've built lots of other suits to test lots of other capabilities. It's been a real heritage of learning and development.
We proactively work with companies to understand their challenges and opportunities and see how our innovative ideas and technologies can help them meet those so they can grow their businesses, create new jobs.
So when you think about 60 years of NASA's history, how it has benefited all of humanity and changed the human condition on Earth, the way we communicate, the way we navigate, the way we produce food, the way we produce energy, the way we do disaster relief, the way we predict weather, the way we understand climate. We are all dependent on space for our everyday lives. All of these capabilities, all of these technologies, all of these things that have improved human life on Earth are available because of a trail that was blazed by NASA. And I think that's really what we do.
And if that's what we did in the first 60 years, what do we have coming up? And I will say that one of the things that I heard is the fact that I forgot how many million things it'll do in 1 second with SLS. Somebody had mentioned about going to Kennedy Space Center for a field trip. Are there launches there? There are launches at Kennedy. Matter of fact, this fall appears to be a very exciting time, both with test for commercial crew, Boeing and SpaceX. But I'll put the list over. I follow Spaceflight Now. They're not associated with NASA. They're independent. But that's just what I personally do. I'm not endorsing them. I'm just telling you to keep up with flight schedules. I use their launch schedule there. I know there's a way you can be a member. I'm not a member. I just use the free stuff. It covers not only NASA, Kennedy, Wallops, Vandenberg, but it covers ULA, SpaceX, and even some international places around the world as well. So if that's a resource you'd like to take care of, I'm sure you can also Google and find that information out as well. But that's just what I do as far as launches are concerned. But we're not really talking about launches today, so I'll put our focus back on the webinar and say our agenda today, we're going to first look at robotics and telerobotics, specifically NASA robotic projects, the Canadarm and Robonaut. We'll have an end effector activity. A lot of times whenever we talk about robotics within the classroom, that's usually somewhat expensive endeavor. I have an activity for you today that we'll give you some economical ways to bring robotics into your classroom. Then we'll look at the engineering design process, highlighting the NASA best activity called telerobotics, where you can design and build an obstacle course and then test that with, and I'll say rovers. If you could see me, I've got that in air quotes, because you can do it for rovers, you can do it with humans, and then we'll also show the connections to NGSS and Common Core. One of the things that I like to do is, well, I love to show you these absolutely amazing, wonderful technology items such as Robonaut or the Canadarm. We'll even take a look at a robot that's picking through ice. To bring one of those into the classroom is an understatement of expensive. However, and I will answer that question of what is telerobotics as we go through this webinar. Great question. But I also want to have practical applications that you can do in the classroom with your students. So it's not just a data dump about knowledge, but it's practical applications and activities that you can do with your students in the class. So while there may be high cost and extremely expensive robots or supplies that you could get, we'll also do some that hopefully you commonly have either just laying around the house or laying around the classroom. So what is a robot? A robot is a machine that has to meet 3 conditions to be considered a robot. It has to sense, think, and act. And it can be fun to have your students try to decide what things are robotic. Is a computer program a robot? Can it sense? Can it think? Can it act? Well, it can, meet the requirements of sensing, maybe through taking in data or performing calculations so that it could possibly think. But the computer program itself does not exactly move, so it doesn't really act. Therefore, it's not a robot. What about a vacuum cleaner? The ones that clean your floor on their own, or other machines that you may have encountered. And this is a great opening activity for your students, whether they're kindergarten or in 12th grade, to really grapple with the idea of what is a robot and what does it take to be classified as a robot. And while, here I've narrowed, succinctly put it as sense, think, and act, within your class, that's a great opportunity for you guys to kind of decide as a class, what meets that standard and what counts, what doesn't count, and do that on your own. Telerobotics, as Tejas had asked about, it's a special field of study within robotics. NASA's Deep Space Network uses it to remotely control a variety of robotic arms, rovers, and devices. These robots make it possible for NASA to take routine, highly repetitive, dangerous, and or even long duration tasks out of human hands, and allows us to improve and hasten human space exploration missions to new destinations. And one of the things that I'll talk about, we know the word robotics. So what does tele mean? Well, if you think about working, in this pandemic, we've heard a lot about teleworking. And teleworking is working from a distance. So if I were to sum up what is telerobotics, well, it's doing robotics from a distance. But that's, my simplified explanation of it. You can see the more complex one there on the screen. So in talking about those telerobotics, I want to show you a video about exploring oceans in the world. The future of telerobotics. Jet Propulsion Laboratory in California has been working on this. They looked at the ice fishing on Jupiter's moon Europa. And so let's take a look at this here as we search out for life beyond Earth and the needs for the robots. Again, I'm going to, the Mars rover would be an example of telerobotics. So here's the video. The link for it is in the chat, but I'm hopeful that there's no issues and you'll be able just to watch. exciting. The question was asked what Juno is. Juno is a mission that was launched in August of 2011 to Jupiter, and it in particular was exploring Jupiter's moons. If you have issues seeing something or issues with the audio during this presentation, one of the easiest ways to fix it is to log off and come back in. I find that logging out and coming back in solves 95, if not more, % of the problems that there are audio, video tech-wise with Adobe Connect. And a lot of times it has to do with the strength of our internet. Does Juno use telerobotics? Juno would be a satellite that was sent. So you'd have to go back and look at the definition of telerobotics. The satellite is circling. So deep space network to provide a variety of robotic arms, rovers, and devices. And with Juno being a satellite, I don't know that I would classify that as telerobotics, but I could be incorrect. I haven't considered that process before. Moving beyond telerobotics and specifically looking at the Canadarm, and that was provided by our northern neighbors. It's better known as an RMS. Well, it's better known as a Canadarm. Another name for the Canadarm is RMS, or Remote Manipulator System. It first flew November 13th of 1981. That's almost 40 years ago. Oh my goodness. The arm has 6 joints. If I did my math right, that's 40 years. Yeah. 6 joints, the original one, 2 in the shoulder, 1 in the elbow, 3 in the wrist. And in space, it could lift more than 586,000 pounds. The 500-foot-long arm is accurate enough to put a peg in a hole, giving 61 thousandths of an inch clearance. I would say that would make it both precise and accurate. And while that was the first Canadarm, in April of 2001, which is 2 years and 2 months ago, we launched Canadarm 2 on board to the space station. And unlike Canadarm on the shuttle, Canadarm 2 is not permanently anchored at one end. The design gives Canadarm 2 the ability to kind of walk around the space station. Canadarm 2 moves up and forth, or up and down, end over end to fixtures placed around the station exterior. Each fixture provides the arm with power and a computer or video link that the astronauts can control from inside. In the notes section of today's PowerPoint, whenever you receive that, you will see that there's additional links and information that you can share with there as well. And with the new Canadarm 2, there's 7 degrees of freedom, 3 at the shoulder, 1 at the elbow, and 3 at the wrist. So moving quite along there. Today, one of the things that we're going to talk about is called an end effector. And you'll notice that little circle there, what shows the latching end effector, LEE. That's what we're going to talk about, your students actually building one of those today, an end effector. So the Canadarm, even though we're coming up on 40 years, they have a celebration video for their 30th anniversary. And I want to share that with you because it shares so much of the success that the Canadarm has had over the 30 years in Canadarm 2. quite amazing what has been accomplished in 30 years, when at this point, 40 years, but absolutely amazing with what's out there. The next item I want to highlight today is Robonaut 2. And Robonaut 2 is the first humanoid in space. And his primary job was demonstrating to engineers how dexterous robots behave in space. The hope is that through upgrades and advancements, it could be one day venture outside the station and help spacewalkers make repairs or additions to the station or perform scientific work. R2 also has a task board on which he practices flipping different gears so that we can understand different ways that he can be used. And I'll show you some pictures of that later. And while we called him Robonaut 2, over here to the left, you have Robonaut 1. Of course, whenever Robonaut first began in 1997, we just called it Robonaut. We really didn't call it Robonaut 1. But there on the left is Robonaut 1 with wheels. On the right is Robonaut 2 with legs. You'll see that those legs are incredibly different than its arms. Part of the idea about building a humanoid robot was that it could assist astronauts like another pair of hands, either for jobs that were too dangerous for crew members or too mundane. The result with Robonaut 1 was a human-like prototype of a robot that could perform maintenance tasks or be mounted on a set of wheels, like you see there, to explore distant destinations. Through 2006, Robonaut 1 performed numerous experiments in a variety of laboratory and field test environments, providing that the concept of robotic assistance was indeed valid. And in 2006, General Motors expressed an interest in the project. They'd been developing their own dexterous robots, and after seeing what NASA had already accomplished, GM proposed teaming up. And so you'll see the difference between Robonaut 1 and Robonaut 2 is that there is a GM shield, or the GM logo. Let me see if I can go back to this one. There you can see the GM on the robot. There was a SpaceX agreement in 2007 between GM and NASA, and in February of 2010, Robonaut 2 was unveiled. It was a faster, more dexterous, more technologically advanced humanoid robot. Its potential was quickly recognized, and space was made available on Space Shuttle Discovery's final mission in July of 2011 to send it on board the space station, making both history as the first actually, if it was Discovery's final mission, it would have been in July. That would have been like in January or February, would have been STS-133. But legs now allow R2, Robonaut 2, to move around on board the space station. Those robotic legs have been built and sent, and it's just absolutely amazing to see what it can do. Give you some more details about Robonaut 2 on this next slide. It's about 8 foot tall. In the space missions, is there a difference between Robonauts and cobots? I'm not sure what a cobot is, unless that's a typo on my part. So sorry about that. But Robonaut is the name with which NASA has named our humanoid robots. It weighs almost 500 pounds. Again, it's almost 8 foot tall. In particular, there's 3 processors, and it's got 58 degrees of freedom total with its legs, and the limb speed is up to 7 feet per second. And I'll also like to point out that on the end of its feet, or where its feet would be, there are end effectors, and those grippers can grasp ISS handrails. And whenever we do a little bit later on, we'll talk about the activity that you can do with your students where they can actually make an end effector. That's basically what's on the end of Robonaut 2's feet there. In space missions, it's okay. When will Robonaut be chosen for an important mission? Well, I would say it's already been chosen for an important mission. It's already been to the International Space Station, and just the process of research and figuring out where we go and what the next steps are, go on. I don't know anything about Astro B, so I'm gonna, if we can focus on the questions in terms of making sure that, as far as I'm not opposed to the questions about, what did you say, cobots, or, let's save that question to the end, and maybe we can do some research and find out what that is. I'm not familiar with that. As I stated, the robot is meant to help humans to do tasks that can be repetitive or dangerous. And so here is a video of Robonaut 2 actually doing some board testing. And so you can see EVA task board testing there. And part of the goal there is to be able to assist the crews in doing especially repetitive jobs. One of the reasons I think that GM wanted to be a part is on the assembly line, there's a lot of repetitive jobs, and we know that repeatedly doing the same task over and over again can lead to muscle damage, such as carpal tunnel syndrome or tennis elbow. And so if we can make that easier, not just for our astronauts, but for humans in general, part of the reason why GM wanted to be a part. And then the other thing I would say is being able to do, especially if we can get them to be able to do spacewalks. Whenever you go outside that space station, there's a lot of risk involved, and that's just an understatement. And excellent. Thank you for sharing that information about AstroB. Again, I'm not familiar with it. So as you can see here, Robonaut is working on opening and closing that. And of course, there's people giving instructions and so forth. It's just amazing to think that a humanoid could perform tasks like that make it appear, in my opinion, so much like a human. So Canadarm, just more stats here. You've got the length, the boom diameter, again, the end effector, and we will talk specifically about that. The wrist joint with pitch, yaw, and roll, which gives you 3 degrees of freedom. The elbow joint, which allows it to bend, so 1 degree of freedom. And then the shoulder joint, again, 3 degrees of freedom with pitch, yaw, and roll. And yes, pitch, yaw, and roll, those are the 3 motions that you have while flying. So if you were to condense down what the Canadarm looks like, you can see here the translation hand controller gives you additional options as far as motions for left, right, up, down, back, and forth, as well as rotational hand control, which is pitch, yaw, and roll. Again, I'll point out that there is a little end effector. And I keep talking about the end effector because that's the activity that I'm going to give you for your to do within the classroom. So speaking of that end effector, now here you can see the Canadarm 2 on board. It's attached to the truss beam or the mobile transporter, which allows it to go up and down the ISS. So the part of the Robonaut arm that grabs objects is called the end effector. It's a wire snare device that's designed to fit over special grapple fixtures. Think knobbed pins that were on the shuttle and are on the ISS and ISS modules. It's a mechanical hand with a cylinder. It contains 3 cables, again, like a snare. I'll show you a better picture of it in a second. And those cables become rigid with enough force to prevent the capture object from slipping loose. And so the activity that we're going to do, the end effector activity to create this, is styrofoam coffee cups. You'll need 2 per team. You need 2 coffee styrofoam cups to make an end effector. You want about 12 centimeter pieces of string. You'll need 3 of them, so 36 centimeters total. Some cellophane tape, plastic knives, and a straw. And I'll also say you can have other smaller devices that can be picked up. No, as I've already shared, there is on board the ISS. I know that the Canadarm 2 is on board the ISS. So I'm going to say yes, that there's only one there, because I know that the other Canadarm was used on board the shuttle. So to my knowledge, there is only one Canadarm on board the ISS. But if somebody wants to do a quick Google search and confirm or contradict, I'd be fine with that too. This is what the ISS end effector looks like. So again, the views of the end effector. Over on the left, you can see where it's open. Over on the right, you can see that wire snare. The end effector is slid over a grapple without touching it and imparting a force. And then the snare is closed around the bottom. And then that way, whenever you pull up on it, the nodes of the grapple fixture align and it latches a hard mate between the two objects. So go on here, and there you can see whenever you close the end effector what that snare actually looks like. And so what I want to talk about before we go into making this end effector, I'm not sure. I would have to do a Google search to see where the Canadarm is. But here is a video about the end effector, and we will take a look at that. Actually, it's not a video about the end effector. This is a video about the best engineering design process, and we are looking at how engineering is everywhere. And since we're going to do an engineering activity, here's an idea about where you can find engineering. All right, and some of the other questions that were asked regarding Canadarm, I did a quick search while you were watching the video. The Canadarm is retired and currently on display at the Canada's Aviation and Space Museum in Ottawa, Ontario. And as I talked about earlier, Canada 2 is the one that's on board the ISS. So as to there being 5 Canadarms in total, I'm not sure what those are or where those are. That's a little bit beyond my scope of covering for today. So back to focus on the engineering design process with the end effector activity. So this is what you're going to start out with. Those 2 styrofoam cups, tape, 3 pieces of string, a ruler, and of course if it says NASA ruler, that's always a positive thing too, and then a knife. Make the end effector. You nest 2 cups together. You cut through both cups and smooth the cut edges by scraping them with the knife edge. Now, I will say that in making the cut, that the cups are nested together. You don't cut one cup and then cut the other. You put them together, and you'll understand why in a minute. If you are dealing with kindergartners, first graders, and you don't want them using the knife, that might be a good idea as the adult to do this yourself. Or if you just in general don't want to deal with a quote knife in the classroom, you might want to go ahead and have that pre-cut. But very simple and easy to do. As for the size of the cups, just make sure they're both the same size. So whenever you take and you cut those 2, this is what you end up with. So you've got a side view there on the left and a tall view there on the right. So you set the ring with the cut end facing up on the table in front of you, and you're going to cut those 3 12-centimeter lengths of string. Tape the end of the first string on the inside of the inner cup just below the cup edge. Tape the other end of the string to the outside, but I will say on the outside of the cup, don't press those tapes down tightly yet, and then repeat that for each of the strings. and a third of the way. So you're looking at basically 12, 4, and 8 positions. And so this is also a way to mathematically bring some math into your classroom and talk about the different measurements. And you can see here on the left, they've taped it on the inside, but they haven't taped it on the outside yet. So as you tape it on the outside of the ring, again, don't tape it securely just yet, because what you want to do, a second, is that's what it looks like. And then what you're going to want to do is you want an open position. And so while holding the rim of the inner cup, rotate the outer cup. And you want to do this until the strings cross each other. So as you first start to turn, you can see the middle part there where there's a gaping hole in the middle. That's not really what you want. This isn't what you want. You want it to be to where it's continue rotating until it closes the snare. Now, the strings will have some slack in them. I've made several of these, and in making them, what you want to do is to make sure that by one twist it closes. So if in one twist it doesn't close, then pull the strings outside until they straighten and intersect exactly. I've had some people take and they turn it like 4 or 5 times before you get that nice tight snare. Well, that's a waste of energy. It's also not efficient and takes up more time. You literally just want to turn it once to close it and then turn it back in order to open it. So, and that's one of the reasons why we don't do the solid tape down to begin with. So there's an example of it closed. Again, maybe not the tightest there, but you can see how that it would keep things out. And then you can also see the comparison between what we created versus what the real end effector looks like. So now that you have your end effector created, use the end effector to pick up a straw. Have someone hold the straw upright. Open the end of the end effector so that the strings are not crossing each other. Slip the end effector over the straw so that the straw extends down and the center and not necessarily through any of the loops. And then rotate the outer cup until the strings grasp the straw so that you can pick up that straw. And so here is a video about Valkyrie, and you can definitely see the advancements that have been made. There's a few minutes left in that, or a few seconds left in that video, but I'm going to stop there for the sake of time just to say, wow, the advancements that are being made. I was able to meet Robonaut 1, Robonaut 2, and also Valkyrie there on your right. So just absolutely amazing is what's out there. Robonaut 2, he was programmed such that whenever I grabbed his hand, there was a certain level of force that once he felt it, he automatically squeezed my hand and then took his arm and moved it up and down as if he was giving a handshake. Absolutely amazing as far as what's out there. There's also Robonaut glove, Robo gloves, and part of this here was with GM, and we'll watch that here.
For more than 50 years, scientists and engineers at NASA's Johnson Space Center have pioneered breakthroughs in medicine, computing, thermal materials, and systems engineering. NASA technologies are innovative solutions that solve complex problems. These patented core technologies are available through a license agreement that can enable entrepreneurs to create new products and new opportunities for business.
So this is RoboGlove, a robotic system that was developed between NASA, General Motors, a spin-off of the Robonaut 2 technology that was built into the Robonaut 2 hand and is powered based on Robonaut actuation and an external power supply. The primary application that we were developing it for was for the heavily repetitive tasks. So the best one that came to mind was assembly line workers, where you're doing a task repetitively throughout the day, every 30 to 40 seconds at a time. Some of these tasks requiring both high levels of dexterity and high levels of hand strength. RoboGlove is a separate entity. It's kind of independent of everything. The one thing that is needed is battery power. We currently have a modular battery that plugs into a power case that would fit onto the user's belt. This single unit can power 2 gloves for an 8-hour shift. The inside of the RoboGlove, we have a set of actuators, 3 of them here, which pull on synthetic tendons that run through the glove out to the fingers. We have a microcontroller, a set of sensors within the fingertips, as well as back here at the microcontroller, allow the operator to tell the glove when to close, how much to close by, and when to open back up. RoboGlove is currently set up to be just in flexure, so it just holds the hand in closure. So any task that is needing to be grasped, held for long periods of time, somebody who is handling heavy equipment, moving things around, where they're picking objects up, placing them somewhere, any type of situation where a normal human is working around a task that is continuous, repetitive, high hand strength, then this is an application that works well.
The NASA GM RoboGlove is a patented technology available for use through a license agreement with NASA. RoboGlove can benefit a wide range of applications and uses that can be sold to a wide range of markets. To find out more about RoboGlove and other technology license opportunities, visit technology.jsc.nasa.gov.
So you can definitely see using the information for GM on a assembly line, how that would be very useful. Check out more videos at Robonaut. There's a video there for the gallery. The question, why are Robonauts not using in human space exploration missions, like sending them? Well, we aren't sending humans to Mars yet. So, and the reason I would say we have sent robots to Mars, I mean, that's what we've done with our rovers. Those rovers are they're a type of robot. They're a robot on wheels. We don't have a need for them to look like humans. We need them to be able to do the science. So beyond that, I would say I think we are already doing that. I think we have those on Mars. We've also sent a rover to an asteroid. So sample robots that you can use within your classroom, the Spark, the Astro Bees, the Car, the Bolt. And so while these may not be economical, you can also use your little humans as robots. And I'll talk more about that as we go. And I know we're getting tight on time here. So for BEST is the engineering design process, and we use the ask, imagine, plan, create, test, improve, and then share. And so we use this process to solve problems. And there's a video on the BEST, but I'm going to, I guess we will go ahead and show that. It's just a little intro. So let me show you that here. And there's a whole series of BEST activities. And of course, BEST stands for Beginning Education, Science, and Technology. And I'll talk more about that after this video.
Hi, I'm Don Higdon. I'm a senior instructional designer with the University of Maryland, Baltimore County. NASA needs engineers. NASA engineers are involved in a wide array of activities, from rockets to robots to satellites. Now, the key to getting more engineers is to engage students when they're young. So we've designed a series of fun STEM activities that will engage them, and more importantly, help them see engineering as a disciplined process. Remember, STEM is science, technology, engineering, and mathematics. Our activities will integrate all of these. Now, we've adopted from the Boston Museum of Science their engineering design plan as our model. The model is simple and intuitive. It involves 6 steps. The students ask questions. They imagine possible solutions. They plan out a design. They create and construct a working model. Then they experiment and test that model. And lastly, they revise and try to improve that model. Now, perhaps the best way to understand this is to actually do it. So we've chosen an example to show this. Sending a rocket to the moon carrying a satellite. But before we walk through the process, let's look at one possible model and the materials the students have to work with. So, here's an example of a satellite that the students might build. Here's a straw that attaches to the satellite and guides it. Here's a rocket that makes the whole system go. Here are some materials we give to the students to help build the whole system. That's the basic idea. So let's start walking through the process.
We are using the engineering design. We do apply to NGSS. There are learning objectives and also Common Core. Yes, OOSBOTs would be another cool choice, especially for the little ones. But one of the things that I was saying is that your challenge is to design, create, and test a program that successfully moves a robot through a simulated terrain. We don't dictate what that robot is. So that robot could be, an OOSBOT. It could be one of the Sparks or the Bolts or one of the B-Bots. It could also be one of your little humanoids, aka students in your classroom. And that student, instead of thinking for themselves, has to take orders from the program or the computer that is written. So the first objective is to design a course. And so with that, since it is an engineering design challenge, there are both design requirements and constraints. The requirements is that you want to cover as much area as possible. You want to accomplish it in as little time as possible. And the rover, or whatever it is that you're using for your robot, should avoid obstacles in the path. The design constraints is that the students can only use the materials that have been provided to create the simulated terrain and path. And you say, well, what are those items? And I'll say, as an educator, what do you have available? For me, I've done this in the classroom, and I allowed students that, as far as the materials provided, we moved all of the chairs and desks to one side of the room so that we had an open classroom. And the materials that they were allowed to create the simulated terrain and path were the desk and tables that we had moved to the other side of the classroom. The other design constraint is that your robot must be able to accept and execute the program for the path you design. To complete the mission, we are using the engineering design process. So you start with ask, imagine, plan. So that's what questions do you have? What do you need? What obstacles are you going to encounter? Show a flow chart. Remember that a robot has to sense, think, and act through the challenge area. Once that's been approved, they will create their program. They will test and run that program to complete the data table, and then of course improve so they can revise the rover. And again, when I say rover, robot, what have you, and program new modifications and share. So when you create your program, this is an outline for the students. I have people that are raising questions. You're more than welcome to put the questions in the chat box. I don't have any other way for you to, you guys do not have the ability to talk, so you'll just have to put it in the chat main. In creating the program, they'll first draw a detailed sketch of the path the robot will take. They'll label the components, including measurements. They'll create a flowchart or pseudocode that describes how your robot will navigate the path. And then whether it's a computer or a mobile device, or whether it's on a tablet and they're just giving instructions to a human robot, that pseudocode into the language for robots to understand. And you can see there, you'll include the commands, and the teacher, as the teacher, you decide whether they can submit the code to try it out, or if the teacher has to give the approval first. And of course, the teacher will instruct whether this needs to be done electronically or with a printout. So there are student worksheets so that you can look at the data tables, both the time required as well as the testing area, observations they have, change or justifications, and then a final design summary. There's also a quality assurance form to make sure that they are meeting the criteria as well as the evaluation. They can talk about strengths and weaknesses, and then talk about judgment. Did it meet all the design constraints and requirements, some or none? And then also, who's it inspected by? And then some follow-up questions, so that discussion questions for the students after the fact. When writing a program for a robot, some things to remind them: how do you tell the robot to turn, go forward, backwards, or stop? How do you know how far the robot needs to go? Once you know how far it needs to go, how do you tell your robot to go that? How can you get your robot out of a jam if something goes wrong? This is known as failing gracefully rather than crashing. And so, you know, how you use, how can you ensure that the robot will do what it's supposed to do before you send it to the challenge area? Remember, NASA has to be sure its robots work before they are sent to distant worlds. Could you imagine us sending a robot to Mars and once it gets there, it doesn't work? Although I will say that we sent a space telescope into space, and it took fuzzy pictures. So let me go ahead and wrap this up, and then I'll come back for your question there, Elena. Testing area. Make sure that there's only one person in the testing area at a time. Make sure you're cautious about trip hazards. There should be team member that are required to clean up the testing area, and team members are required to take all materials with them when leaving. They want to make sure that they have a technical report. NASA engineers write technical reports for many reasons, including documentation of experiments and designs. A typical technical report that documents the steps of the engineering design process include these particular sections. There's also an opportunity for a digital badge on the Robonaut, and that is on the Human Exploration and Telerobotics. So if you do this activity, you can earn that telerobotics app. Deep thoughts. These are just some additional information for the sake of time. I'm going to move forward with that, with alternative ideas, common misconceptions. I think that's important to read. But I do want to go ahead and show you that at the end, I've added some group roles. This really helps, in my opinion, as far as keeping things moving and concise. And there's also, for the engineering design, if you're not familiar with the BEST program, they've got a video for each one of those. And so each one of those videos are embedded within the PowerPoint. But for the sake of time today, have a great day. We will see you all later.